topic. This is in section 2.8, and this is on differentiability. All right, differentiability of a function. All right, differentiability of a function. We're basically, up until now, we said, does a limit exist? And we looked at the function. We determined if a limit exists. We determined whether or not the function was continuous. Now we're looking whether or not a function is differentiable at a point. All right, so that's what we're looking at. Is a function differentiable at a point? So I'll start with this function. There we go. That's some polynomial, everyone. This is just, I do want to point out, it's a nice, smooth polynomial. But where is this function differentiable? The answer is everywhere. So this polynomial here, you don't even need the equation. You can look at the image. This is the x-axis, that's the y-axis. But this polynomial is differentiable everywhere. Everywhere. And so you go, what do you mean by differentiable? The derivative of f exists everywhere. That's what I mean. And we did two-sided limits. That's f of x. We did two-sided limits. Well, now you're thinking about like how the slope from the left equals the slope from the right at every point. And I can just pick a point like right there. Is the slope as it approaches from the left side matching the slope as it approaches from the right side right there? Yeah. Are the slopes equal coming from the left and from the right? Because slope of a tangent line to a curve is a derivative. I'll say it again, that's what a derivative is. It's the slope of a tangent line to a curve.
If one goes up and the other one comes down.
Then it's no good. Very good. So that's what we're going to focus on. I like how you think. That's easy. It's nice, everyone. It's nice and smooth everywhere. So that goes for all polynomials. They're going to be differentiable everywhere. So we got to focus on when are they not differentiable. And you figured out one thing. You said if you had something like this, something came up like this and something went like that, right? Ooh, thanks. Yeah, you could just put it right there. Thanks for doing that. She had about 3 hours of traffic. Ooh, yeah. Hey, so you nailed it. So that's what we're going to focus on now. And all polynomials, I guess they're going to be differentiable everywhere. Let's focus on where is the function not differentiable. Then we'll be good. So where are functions not differentiable? And you go, what's differentiable mean? The derivative exists at the point. You go, what's a derivative? So we got to get all these words down. Derivative, we're talking about the slope of a tangent line to the curve. And so again, just before I erase this, like even at that point right there, does everyone agree? Like the slope from that side matches the slope from that side right at that point. Yeah? And that'll exist everywhere in this group. So we go right to it. All right. Differentiability function. Where is a function not differentiable? Or when? I should change where to when. Talk about the different occurrences. When is a function not differentiable? All right. I'm going to start out with yours. You did something like, they came up like this, and then they came up like that. Oh, those slopes are not equal at that point. So it wouldn't be differentiable at that point. So we're going to start out with C, corners. C for corners. You got a corner in a graph. You nailed it. Now, if you got a graph, you got something like this, like a little corner, like a V somewhere. Yeah, at that point right there, at any corner, at that location right there, let's say there's an x value for this dot, the function is not differentiable at that point. Do you all agree? We go, why? Because does the slope from the left of that dot match the slope from the right? No. So very good. I'm going to put another word for C.
Is there a way to do that?
Let me finish this up, and then I'll get your question. I like this with corners, but let's also put cusps. And I'm going to show you what a cusp is. A cusp looks like this. It's not really a V, but it might come up like this, and then it comes up like that from that side. Now, can you see this is really, really steep and positive, but this is really, really steep and negative? And so that's another one. Oh, go ahead.
Is there a way to prove it mathematically?
Absolutely. Yeah. It's just looking at, remember, he does math proof. So what you have to do is, remember the derivative definition? I'm going to write it down. What's the definition of a derivative? It equals the limit as h approaches 0 of f of x plus h minus f of x all over h. And you'd have to do this from either side. So you'd have to do like a plus or minus here. So remember that from the left side and the right side? So I'm going to write this another way. Here's another way of looking at f prime of x. You can say f prime of s is the limit as x approaches a of f of x minus f of a all over x minus a. Remember we were talking about how this, I'll hide this. Remember this was the secant slope? And we add that and you go, you get the slope of a tangent. So you would do this, but then you do a left side and a right side. And that's your mathematical proof. So that was a good question, because could you do it, man, like, how do you do this in an elegant way? Mathematics is interesting, like with notation. You'd have to do all that work, but you'd have to do a negative for the left side, then a positive right side, and make sure those slopes what match. Very good. Hey, so when C, corners, cuts, I got 2 more letters for you. The next one is V. V for vertical tangents. V for vertical tangents. All right. What do we mean by vertical tangents? I'm going to give you an example of a function. So and here's my example for vertical tangents. It'd be something that did this. The graph went up like this. Then it looped over like this. It actually changes concavity. Does anybody know that word concavity? This is like, it went from concave up, and then the concave down. But everyone, right there at that one instant, if you think about the slope of a tangent line here, 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 but right there, the slope of a tangent line to that curve would be totally vertical. What's the slope of a line like that? It's undefined, yeah. And so that's why we're saying, oh, then the slope would be undefined. And that's why we're saying that's another place where a function is not differentiable. You go right here at this location at an instant, and we look at the slope of this line. The slope would be totally vertical, and it's undefined. So V for vertical tangents. I do want to point out sometimes if you're just given an image, it's hard to tell. So don't worry about that. If you're unable to, you might be like, I can't tell if it's really a vertical tangent, and maybe it's just really steep. And I understand that. Got one more letter, J. I don't know, does JVC still make equipment, like electronic equipment? Oh, good. So that's what I use. I like this acronym, JVC. Acronyms help us remember things, you know, like mnemonic devices, JVCs. Where is a function not differentiable? JVC, V for vertical tangent, C for the corner cusp that you hit on. J stands for jump discontinuities. Jumps and discontinuities. J for jump, or jumps. Well, I can give you some examples of those, everyone. What's a jump discontinuity? Something like this. Oh, the graph went like this, stopped here, started here. Yeah. That's one example of a jump discontinuity. See how it jumped? Right? Basically, I'm talking discontinuity where it's not continuous. Here's another one. And when this is a jump discontinuity. Hole, then it continues like that, but there's a hole there. So I'm talking about right at this location. The function is not differentiable here. Right here, the function is not differentiable. Cool? Right there, there just can't be any one. Jumps. So the acronym JVC, J for jump discontinuities, V for vertical tangents, C for corners and cusps, and we're able to identify exactly where functions are not differentiable. He went on to the algorithm. He said, what about math proof? If you wanted to really prove it, you could go and dive into the function I give you and show this from the left and right side. Cool. So in my next exercise, I'm going to draw a graph. I'll put some numbers down. I was wondering if you could identify all the x values where the function is not differentiable. Good news, you'll see practice problems that I chose in the textbook on this. But I'm just going to draw a picture. I'll go left to right. I guess I can do it over here. I do it right here? Would it hit it? Was it too far away? Awesome, I'll do it right here. Now we can leave that up. All right. Here's my graph. All right, this graph does this. Let's see, it comes down like this. Let me put a bunch of x values down. Okay, that's good. 1, 2, 3, 4, 5, 6, 7 is the x-axis. -1, -2, -3, -4, -5, -6, -7, -8, -9. We're going to make sure these line up though, because I know you all are already identifying where this function is not differentiable. I'll just call this f of x. I mean, this does pass the vertical line test, right everyone? Make sure that's just, I'll just put an arrow there. Maybe I can make this look a little bit better. I want that to be smooth. I'm trying to make the thing come up. There we go. That'll work. That will work. At this location right there, let me make sure that lines up. That's it. X equal to -5. Right there. All right, let's see if we can do this. So where is this function not differentiable? Not differentiable. Question mark. Just list the x values. As you can tell, I didn't put any y values down. Anybody got one? X equal to -5, right there. Boom. Corner or cusp, right? If you're looking, is that a corner or is it a cusp? It's one of those. And x equal to -5. I'll put a comma because there are more, right? What's another one? -2, another corner or cusp? Any more? 2, +2. And maybe that's it, but do you see one where perhaps it is? Where? 4. What's it look like is going on at x equal to 4? Yeah, but see, again, it's like I'd have to make a really good sketch. I was trying to show that this thing got really, really what? Yep, totally vertical. Totally vertical here. So if I can improve that, make this look a little bit better. That's smooth right there. So it does look like there, when an x equal to 4, there is a vertical tangent right here. So we can mark this thing up. Right there. There's a vertical tangent. This was a jump, right? Jump discontinuity. This was a corner, this was a corner. Awesome. Everyone okay with that? Put a problem like this on the next test. Graph, but yeah, it shows. No JVCs, right? What we're saying is the function is not differentiable at JVCs. Hey, you'll laugh. A student who graduated 10 years ago on Facebook wrote me a message, like within the last year, and he just, that was what he wrote. He's like, JVC, function not differentiable. It's like, that's what you remember? All that calculus. For some reason you remember this. I was cracking up. It's like, you remember that? Ah, I guess it works. I guess it works. Hey, we won't do a proof for this problem, but I do want you to think about, I'm going to put something on the board, I'm going to put a piecewise function, and I'm going to ask you about three things. Does the limit exist? Is the function continuous at the point? And is the function differentiable at the point? All right? Now, before I do that, I think we should put a phrase with the words differentiable, continuous, and limit. We should make a little diagram for that. So how about this? Washington, D.C. is lovely. Will that work? Washington, D.C. is lovely. That's not as cool as JVC. But DCL, what I'm saying is, if a function is differentiable at a point, that arrow means then. Then the function has to be what? Continuous at the point, which also implies that the function has to have the limit existing at the point. The only thing is, can you reverse this order? No, it wouldn't always be necessarily true, so make sure you don't reverse it. But if a function is differentiable, then it must be what? Yep, at that point. If a function is differentiable at a point, then the function must be continuous at the point. If a function is continuous at a point, then the limit, the two-sided limit must exist at the point. The only thing is, you can't do this, right? Look, does C imply D always? No, not always. I'm going to put a slash to it. And then might give me an example of a function that's continuous, but it's not differentiable. Watch, I'm going to call it one. To show the counterexample of why we can't say C implies D.
Vertical tangent.
That's a good one. I love that. It says a vertical tangent. You know? He goes, hey, it's continuous here. That was a good one. It's continuous right there. That's nice and continuous, but it's not differentiable. Here's mine. How about the absolute value of x graph? Yeah, like that. That was a good one. How about the y equal absolute value of x graph? We all know what's a v, right? It's continuous right there, but it's